Bismillahirrahmanirrahim. Hello everybody. This is an exercise which concerns sequences. So let UN be real of positive terms, real positive sequence, and we suppose that the nth root of UN converge to L when n goes to plus infinity. Show that if the limit L is less than 1 and greater than or equal to 0, then UN converges to 0. If L is greater than 1, strictly greater than 1, the sequence UN converges to plus infinity. And if L is equal to 1, we cannot say anything. This case is a non-conclusive case. And we finish by applying on this just one example. Next, I will solve many exercises about this case, this kind of convergence. So first, we suppose that the nth root of UN converges to L. This means that for all epsilon greater than 0, there exists a rank n of epsilon from n, such that for all n greater than or equal to n epsilon, this implies that the difference between the nth root of UN and L is less than epsilon. We take off the absolute value, so we will get 0. More precisely, we will get L minus epsilon less than the nth root of UN, which is less than L plus epsilon. But since the UN is positive, so the nth root is positive, we can here just take greater than or equal to 0. We have L less than 1, the first case. So we can find epsilon greater than 0 such that L plus epsilon still less than less than 1. For example, if we take epsilon equal to 1 minus L divided by 2, we will get L, which is less than 1, plus 1 minus L divided by 2. This is equal to L plus 1 divided by 2. Since L is less than 1, as it is in the hypothesis, so L plus 1 is less than 1. This means that we are able to find 1000 epsilon such that L plus epsilon is less than 1. But here we have for all epsilon, we choose epsilon such that this is true. If this is true, what we can write? We can write from here. We can write that UN is less than L plus epsilon power n, which is greater than or equal to 0. And since L plus epsilon is less than 1, when n goes to plus infinity, this goes to 0, which means that squeeze theorem, which means that UN goes to 0. So the first question is done. The second, the case 1L is greater than 0. The same thing. So we have the same thing. Just here. We need more L minus epsilon. We need L minus epsilon. In the first case, we could let L minus epsilon as it is here. If it is negative, so this is greater than or equal to 0. If it is not negative, it is positive, so it is less than this one. And when n goes to plus infinity, this goes to 0, this goes to 0, so un goes to 0. I am sure that you have understand this little small idea. In this case, we don't need this. When L is greater than 1, just this is sufficient. L is strictly greater than 1. As we did with L less than 0, we can find epsilon greater than 0 such that L minus epsilon is still less than 1. No, is still greater than 1. Strictly, we can find 1000 or more epsilon which verifies this strict inequality. In this case, we can have L minus epsilon power n, which is less than un. When n goes to plus infinity, this goes to plus infinity, which means that this goes to plus infinity. This is a first method. We can use the previous result, how we can use it. So here we finish. Second method, for this case, it is sufficient just to prove the first one, to prove the second one. How we can deal? We consider that the nth root converges to L. If L is greater than 1, we consider Vn, which is equal to 1 over un nth, and this new sequence converges to 1 divided by n. But since 1 divided by L, which is L prime, is less than 1, this implies that Vn converges to 0, which means that 1 un converges to 0, and this means that un converges to plus infinity. This is a second method. For L equal to 1, for L equal to 1, we cannot say anything. All possibilities can be true. To answer this question, we can take un equal to n. We proved in a previous video that the nth root of n converges to 1, and in this case un converges to plus infinity. So L is equal to 1. We take Vn, which is equal 1 divided by n. In this case, the nth root of Vn, which is 1, the nth root of n, converges to 1, but Vn converges to 0 when n goes to plus infinity. So this case is non-conclusive. How we can apply this for this example? Find the limit of this sequence. We need to find the limit of 2n squared, n which is squared, n factorial power n. How about the limit? We can use this theorem to answer. So let the nth root So here we take the nth root, which is 2 power n divided by n factorial. We take this one. 2 power n divided by n factorial is equal to 2 times 2 times 2 n times divided by n minus 1 divided by 2 divided by 1. So if we take n greater than 3, then 4, we will have 2 divided by 4 times 2 divided by 3 times 2 divided by 2 times 2 divided by 1. So this is less than or equal 2 times 1, 2 times 1, 2 times all the remainder is less than 2 divided by 3 n minus 2 times. This is a positive sequence, and when n goes to plus infinity, this goes to 0, because 2 divided by 2 over 3 is less than 1. This means that the nth root of the sequence converges to 0, which is equal to n, and since this is equal to 1, this means that this sequence, the limit goes to 0. This ends this video. To the next one, inshallah.